We're now ready to look at Chapter 12 Statistics, Section 12.4, the normal distribution. Don't be scared by the number of objectives that are shown. First, recognize the characteristics of normal distributions. Understand the 68, 95, 99.7 rule. Find scores at a specified number of standard deviations from the mean. Use the 68, 95, 99.7 rule. Convert a data item to a z-score. Understand percentiles and quartiles. Use and interpret margins of error, and recognize that certain distributions are not normal. Normal distribution. This is also called the bell curve or the Gaussian distribution. Normal distribution is bell-shaped and is symmetric about a vertical line through a center. This is shown below. Mean, median, and mode are all equal and located at the center of distribution if it's a bell curve. The shape of the normal distribution depends on the mean and the standard deviation. The three graphs above have the same mean, but they have different standard deviations. As the standard deviation increases, the distribution becomes more spread out, but it retains a symmetric bell curve. Now we're getting into that rule that we referred to. Approximately 68% of the data items fall within one standard deviation of the mean. So over here to the right, that would be the pinkish area. It's one standard deviation to the left and one standard deviation to the right of the mean. Approximately 95% of the data items fall within two standard deviations of the mean. So that would be the pink and the blue. It goes two deviations to the left of the mean and two deviations to the right. Approximately 99.7%, nearly 100% of the data items fall within three standard deviations of the mean. Example 1, finding scores at a specified standard deviation from the mean. Male adult heights in North America are approximately normally distributed with a mean of 70 inches and a standard deviation of 4 inches. Find the height that is 2 standard deviations above the mean. The height is the mean, which we're given 70 inches, plus 2 standard deviations. This is a standard deviation for this particular example would be 4. So we're going to take 2 times 4, and that gives us 78 inches. Example 2, using the rule 68, 95, 99.7. Use the distribution of male adult heights in the figure to find the percentage of men in North America with heights between 66 inches and 74 inches. The rule states that approximately 68% of the data items fall within one standard deviation, 4 of the mean, 70. So the mean minus 1 standard deviation would be 70 minus 1 times 4. Remember, the standard deviation is 4, which is 66. We also have to take plus 1 times the standard deviation. So that'd be 70 plus 1 times 4, which is 74. So 68% of the males have heights between 66 inches and 74 inches. Computing z-scores. A z-score describes how many standard deviations a data item in a normal distribution lies above or below the mean. This z-score can be obtained using this formula. Z-score is equal to data item minus mean divided by standard deviation. Data items above the mean have positive z-scores. Data items below the mean have negative z-scores. And the z-score for the mean is 0. Looking at example 3, we want to compute z-scores. The mean weight of newborn infants is 7 pounds, and the standard deviation is 0.8 pound. The weights of newborn infants are normally distributed as shown to the right. Find the z-score for a weight of 9 pounds. The mean is 7, we're given that. The standard deviation is 0.8. So the z-score, which in this case is written z sub 9 because we're finding it for 9 pounds, is equal to the data item minus mean divided by the standard deviation. That is our formula. The data item is 9 minus the mean is 7. Standard deviation is 0.8. The numerator is 2 divided by 0.8, which is 2.5. That is the z-score. It's positive, which means it's above the mean. Example 4, understanding z-scores. Intelligent quotients, you've heard of IQs on the Standard Binet intelligence test, are normally distributed with a mean of 100 and a standard deviation of 16. What is the IQ corresponding to a z-score of negative 1.5? The negative sign in 1.5 tells us that the IQ is 1.5 standard deviations below the mean. 1.5 is the same as 1.5. So the score is going to be the mean minus 1.5 times the standard deviation. The mean is 100 minus 1.5 times 16, which is the standard deviation. That is 100 minus 24, which is 76. So the IQ corresponding to a z-score of negative 1.5 would be 76. Percentiles and quartiles. If n% of the items in a distribution are less than a particular data item, we say that the data item is in the nth percentile of the distribution. Quartiles. Divide data sets into 4 equal parts. The 25th percentile is the first quartile. The 25% of the data fall below the first quartile. The 50% quartile, the 75% quartile is the third, as you can see in the diagram to the left. So it's divided into 4 parts. Each is 25% of the data. A percentile interpretation for z-scores. Using the z-score in a table, you can find the percentage of data items are less than any data item in a normal distribution. In a normal distribution, the mean, median, and mode all have a corresponding z-score of 0, and they're in the 50th percentile. Thus, 50% of the data items are greater than or equal to the mean, median, and mode. Poles and margins of error. Statisticians use properties of the normal distribution to estimate the probability that a result obtained from a single sample reflects what is truly happening. If n is the sample size, there is a 95% probability that it lies within 1 divided by the square root of n of the true population statistic. Plus or minus the 1 divided by the square root of n times 100% is called the margin of error. Example 5, using and interpreting margin of error. In a random sample of 1,172 children, ages 6 through 14, 17% of the children said getting bossed around is a bad thing about being a kid. We want to verify the margin of error. The solution, the sample size is n is equal to 1,172. That's the number of children. The margin of error is plus or minus 1 divided by square root of n times 100%. So substituting n into our formula, we get plus or minus 1 divided by the square root of 1,172 times 100% is approximately plus or minus 2.9%. Next, we want to write a statement about the percentage of children who feel that getting bossed around is a bad thing about being a kid. There's a 95% probability that the true population percentage lies between 17% minus 2.9%, which is 14.1%, and 17% plus 2.9%, which is 19.9%. And lastly, other kinds of distributions. The graph to the right represents the population distribution of weekly earnings in the United States. There is no upper limit on weekly earnings, so the blue line is going to approach but not touch the x-axis. The relatively few people with a very high weekly income pull the mean income to a value greater than the median. The most frequent income, the mode, occurs toward the low end of the data items. This is called a skewed distribution because a large number of data items are piled up at one end or the other with a tail at the other end. This graph is skewed to the right. And that concludes this lesson.